lot of homework. But the summary of chapter 7 is this. The author explains that in chapter 7, for the rest of the book, okay, chapters 8 through 17, for the rest of the book, we're only going to be doing 2 types of problems, either an estimation problem or a hypothesis testing problem. And to do those types of problems, you need to have an understanding of what a sampling distribution is, and you need to know about sampling variability, which you may already know about. So I want to talk about chapter 8, which is sampling variability and sampling distributions. This chapter is foundational to chapters 9 and 10, very foundational. And then knowing what a sampling distribution is will help you in the coming chapters as well. So right now, I want to get you to wrap your head around what sampling variability is, and then even tougher, get you to wrap your head around what a sampling distribution is. Okay, so I want to give you a couple examples, and then we'll present you with some of the definitions. Okay, first let's talk about sampling variability. Okay, here's the scenario. Okay, suppose that I sent all of you individually over to the library. And I guess in the scenario, you can actually physically go into the library. These days, that's not happening. But suppose you all individually go into the library and randomly select 20 books. And what I'm trying to do is I want you to come up with an estimate for what is the percentage of read books in the library. So what is the actual percentage of read books in the library? So if you all individually went over there and took a random sample, some people might choose to do a simple random sample. Some people are going to do a cluster sample. Some people may do a stratified sample. Okay, so you're going to use probably different sampling techniques, but these will all be, I hope, random sampling techniques. Okay, and suppose I ask you to get a random sample of books, 20 books from the library, and measure what percentage of books are read, okay, as an estimate of P, the actual percentage of read books in the library. Here's the question. Supposing I did that, you're all going to come back with an estimate for P, and that estimate for P, the actual percentage, will be a number that's called P with a hat over it, P hat. Okay, so in this scenario, we want to estimate the value of P, and we're not going to do this by just asking a librarian, they have no idea. And we're not going to do this by examining every single book in the library, okay? But if you get an estimate of this value, you're getting a value of P hat, the percentage of read books from your sample. Now, here's the question. Will you all get the same value for your sample percentage?
No.
And there's a number of reasons why the answer is no. One reason could be, how do you define a read book? Does everybody define a read book the same way? I mean, if it's slightly orange, is that considered red? And, you know, so definitely your P hats will all be different. And one reason may be just because you all define what a red book is differently. Some people are going to include orange books that may look red and to them, etc. Another reason why you will get different values for P hat is because of what's called sampling variability. Sampling variability. The first concept in Chapter 8. And here's your definition of sampling variability. The observed value of a statistic, so that's your observed value from your sample p hat, varies or is different from sample to sample depending on the particular sample selected. Not every sample is going to be strongly representing the population, okay, even if they are random samples, okay, and this variability amongst sample results, right, the fact that you're getting different values for the statistic p hat, the reason that happens is attributed to you're getting a different sample than the next person gets. Okay, so you're not going to get the same value of p hat, and that's because of sampling variability. And we'll take a look at this, but let's come back to it after I do another example. But take a look at, here's your definition of what a sampling distribution is. A sampling distribution of a statistic. Where's my, we need to run through this. All right, I think we need to backtrack a minute. Probably need to backtrack a minute or two, okay? Remember, we're using different symbols for population characteristics than we are for sample statistics. Okay, so remember there's population characteristics like the population average or the population percentage or the population standard deviation. These are all things that are referred to as being parameters. And they're different from sample statistics. And the notation and the symbols that we use are different. And so I'm going to start getting notationally heavy. And so you need to recall these facts, okay? That mu is the symbol we use for population mean. That you probably remember. Oops. And sigma, that's going to be the symbol we use for population standard deviation. And we're going to have a value of p, or we're going to encounter a value of p. That's another parameter. So the types of parameters that we're going to be studying, there's about 6 of them, but here's the first 3. The population mean, standard deviation, and population percentage, which the book calls this a population proportion. And we're going to use these symbols for those, but whenever you take a sample from the population and you find remember that's a subset of the population. If you find the average of the sample, that's going to give you some number x bar, a sample statistic. Right? And if you get a standard deviation of the sample, that's going to be some value s. And if you're going to get a percentage of the sample that has some characteristic, that's giving you a value of what's called p hat, or fat for short. I don't know, p hat, I guess is what's p with a hat over it. So you need to remember and understand the differences between these 6 symbols. Is that clear to you now, or what questions are you having about that? So we're going to work with all of these, but right now, immediately, we're going to be working with these 2 symbols. We've got a population characteristic. In the first example I gave you, P is the actual percentage of read books in the library, and P hat is your percentage of read books from your sample. So we're going to be working with these 2 symbols, these 2 values. You need to know the difference between them. And then on top of that, I apologize. I'm going to introduce some new symbols that are even more confusing and crap. But I want you to always question, always indicate when you are not understanding, and always ask me to give a better explanation or further. Okay, moving forward, please do stop me whenever you have a question, because I don't think there's such a thing as a dumb question in this class. I guess I've heard a couple, but most of the time I'm very grateful that the student has asked the question, and that's because it gives me another opportunity to try to provide more clarity or give an explanation in a different way that does so. Okay. All right. So here's your definition of what a sampling distribution is. This is a general definition, and we're going to get down to specifics because there's different types of sampling distributions, and we're only going to begin by working with one type. So here it is, a sampling distribution of a statistic. So that is a collection of one of these three values, or later there's 6 values, but for now let's focus on these 3. But it's the sampling distribution. It's just a collection or a list of all, well, let's put an explanation right there, of all possible values of the statistic drawn from all possible samples of the same size n. So in the first example, I sent you all over to the library and asked you to take a random sample of 20 books, a value for p hat, the sample percentage of read books, okay? And when you come back here and you give me 32 different values for p hat, that collection of values of p hat is an approximation of this collection, the sampling distribution of p hat. Okay, so that was kind of deep. In this case, the entire collection of sample percentages from all possible samples, and again, we didn't take all possible samples, and in many cases, there's an infinite number of possible samples, but they all have to be of the same size, okay? A sampling distribution, you're going to get a different sampling distribution for every different sample size n. But in the first example, n is 20. Everybody's collected a random sample of 20. So in the first example, the entire collection of sample percentages from all possible samples of random samples of 20 books from the library is called the sampling distribution of p hat. So you can get a different sampling distribution for every single different statistic. For now, let's just talk about these 3, but of course there's other statistics. And to complicate things, if I haven't lost you yet, let me lose you now. God, I shouldn't have said it. Is you're going to get a different sampling distribution for every different value of n. So these are these are facts that I want to come back to and try to get you to wrap your head around with some examples and a visualization or 2. And so that's where I'm going to work now is, yeah, I gave you the definition of sampling distribution, but do I expect you to understand it and have it in the gut right now? No. So let's try to work. I'm going to try to work now to have you be able to digest what this thing is and understand what it is, the sampling distribution. But it's just a list. Okay, so let's go back to, if it was the first example, if it was possible to get the entire collection, then I would have the actual sampling distribution, the actual list of all possible values of p hat. But because there's only like 32 of you in the class, I'm only going to get 32 values of p hat. But if I graph that list of p hats as a dot plot, then I'm going to get a somewhat fair approximation of what the actual sampling distribution looks like. Any questions about that? And I probably lost people, but hopefully I can get you back. All right, so let's give you yet another example, and it's going to come over here. Oh, boy, let me get out of this. So I'm going to have to throw a link down to this, but Rossman and Chance, they have, it's a couple of different people, and they're statisticians, and they did a wonderful job with some computer science graduate students to come up with this applet collection. Am I showing my screen? Oh, I'm not showing my screen. Am I showing it?
Yes.
Okay. Anyway, the Rossman-Chance applet collection, there's a bunch of different applets here. I may use one or two of them, but let me first just do one of them, okay? And it's this example for Reese's Pieces. Okay, so let me zoom in here. Okay, so here's I'm gonna give you an example of a sampling distribution, and we're gonna take a look at the graph. And then I'm going to ask you if you notice anything from that graph that's somewhat striking. Okay, so right here is a picture of a candy, what is it called? Candy dispenser. These, I don't know if they're still there. I don't see them, but these used to be outside of every grocery store and in every fun factory and Chuck E. Cheese. You know, you put a coin in, you twist the knob on the machine, and out from this porthole comes your candy or your bubble gum or your secret coated ring or whatever's in there. So it's a picture of one of those devices that's outside of the grocery store that used to be. My goodness. And they also used to have that one where it was like the horsey that the kids could ride, the little kids could ride. It would rock back and forth. You probably remember this, don't you? I don't know, maybe I'm aging myself. Okay, but going back to the example here, suppose this is that candy machine, and suppose that the actual percentage of orange candies, these are Reese's Pieces right now, but suppose that the actual percentage of orange Reese's Pieces in this device are 50% or 0.5, okay? And now I'm going to draw a random sample, or the applet allows me to draw a random sample of 25 candies from the device here. And what we'd like to do is measure the percentage. I'm going to click this over here to the percentage of, we want to measure what is the percentage of orange from our sample. So we've got a value of P, the actual percentage of orange Reese's Pieces in the device. And when I click on this draw sample, it's going to give me a sample proportion from a random sample of 25 pieces out of the candy device. And so that's going to give me a value of P hat. So there it is. Let's take a sample. Okay, so it took the sample, and it's telling me that the percentage of orange candies in that sample was 52%. And so that percentage, that sample percentage, P hat, was plotted as a single dot right here above on the graph down here, above 52%. You see it? But here's the thing. What I'd like to do is try to approximate or come up with a good representation of the sampling distribution of P hat. which is the entire collection of sample percentages taken from all possible random samples of the same size 25. So here's your definition for the sampling distribution of p hat, or the long way of saying this is the sampling distribution of sample proportions is a list. It's the entire list or collection of sample percentages, values of p hat, that are obtained from all possible random samples of the same size n. In the example I'm showing you, n is 25. And we're going to simulate using the app the graph of the sampling distribution of p hat. This entire, right? If you graph this entire collection or this list of all possible values of sample percentage, if you graph that as a dot plot, you're going to get a good approximation of what the graph of the sampling distribution looks like. Okay, and then the other point is, and this is it's so darn confusing when you're just starting out in this class, but you're going to get it for every different value of sample size, right? If you change, right now in our example, our sample size is 25. And I'm going to use the app to simulate the sampling distribution of p hat for samples of size 25. But if you change this number to a different sample size, say 30, and you rerun the simulation, then you're going to get a different sampling distribution, a different collection, a different list of random sample percentages, and therefore you're going to get a different sampling distribution. So once again, for every different sample size, n, you're going to get a different sampling distribution or a different collection. Okay, fine. Stop me whenever you have questions, okay? So right now, let's go ahead and go back up here. I want to have it take 99 random samples, or I guess I'll do it a little bit slower. Let's have it take 4 more random samples, and each time it takes a random sample, it's going to find a sample percentage, a value of p hat, the percentage of orange Reese's Pieces from the sample, and that value of p hat will be plotted on this dot plot down here that we're going to make as a single dot. So we're going to go ahead and draw 4 more samples, and each time get a sample percentage, a value of p hat, and then we should see 4 more dots down here after the simulation is run. Let's do it now. Oh boy. It's almost like watching paint dry. But anyway, there you go. Of the 5 samples we took thus far, look, you're getting 5 different values for p hat, or the sample percentage. This is an illustration of what sampling variability is, right? The sampling variability. All right, what is it, right? The fact that you're going to get different values for your observed statistic is attributed to the fact that you're not all going to have the same random sample. Okay, so yeah, we could get a sample that has the same percentage as some of these other dots, and maybe if we take more samples, we can find those. Okay, so I'm trying to approximate the sampling distribution of p hat here with a dot plot. And to do that, we would have to have all of the possible samples of the same size. That may not be possible, but if we get a large number of samples, then we can get a pretty good approximation of the sampling distribution graph. So we have we've taken 5 samples. I'm going to have the applet take another 95 samples. each time it takes a random sample, it calculates another value of p hat, a sample percentage of orange candies, and we'll plot that value of p hat on this dot plot down here that we're making. So let's do that now.
So just to confirm, I just want to double check. So a sampling distribution is just the collection of the variables we've collected.
It's the entire collection of all possible values of the statistic. So we are going to be working at first with the sampling distribution of p hat. So this would be the entire collection of sample percentages. But you can get a sampling distribution for a different statistic. X bar is the sample average. Okay? So if, for example, let's go back over here. This is worth doing. Okay, here's all of the words in the Gettysburg Address in this list here, right? It starts out 7 years ago, or 5, right? Okay, so all of the words in the Gettysburg Address are on this list here, and the list, the words are ID'd by number, and notice that they're also collecting the length of each word, so the number of characters in each word, right? The word for has 4 characters in it, the word score has 5, and so on. I want you to hone in on this column for length, character length. What is the average word length or character length for a word in the Gettysburg Address? Well, to get that actual average, right, we just take the average of this length list here. Moreover, you can get what's called the sampling distribution of X bar. Okay, so here's what I'm saying is, suppose that I give you all this column of lengths, and you all take a random sample of lengths, and you take a sample of size 20 measurements randomly selected from this column, and each time you take a sample, you gather a sample average or a sample mean. If we could get all of the possible samples of size 20 and get all of those possible sample means, then we would be getting what's called the sampling distribution, or the entire collection of X bar. The sampling distribution of X bar. So which is the sample statistic, which is the sample mean. So for every different statistic that we have, and yes, I've circled 3 of them, but there's a lot more than that. I'll try not to go too fast here. But for every different statistic, you can even get a sampling distribution of the median. This is the entire collection of medians drawn from all random samples of the same size. So you're going to get a different sampling distribution for every different statistic, and that'll be the entire list of all possible values of that statistics. But they have to be all drawn from the same sample size n, and that's because for every different value of sample size, you're going to get a different sampling distribution graph. Okay, so I'm back, and I wanted to add to what I said about the sampling distribution of X bar. Okay, this would be the entire collection of sample means taken from all possible random samples of the same size. And this is the topic of chapters, I think it's 11 and 12. So we're going to be, so first you need to understand that a sampling distribution is the entire collection of all possible values of a statistic, and that you can get a different sampling distribution for every different statistic. And there's more than just these four. But for now, but in this class, we only look at, I don't know, 5 or 6 of them. And then, of course, to confuse people, well, I don't know if it's explicitly to confuse people. But look, you're going to get a different sampling distribution for every different sample size. Okay, fine. Look, in this section, chapter 8, we are only trying to use or getting you to wrap your head around what the sampling distribution of p-hat is. And going back over here to the example with Rossman Chance, okay. So right now, we've got this candy machine. We know that the actual proportion of orange candies is 50%. And I want to point something out that's important. N is, did we make N 25 on here? I think we did. N is 25. And so you've got 25 trials here. Every time you take a sample, in this context, every time you take a sample of 25 candies, every single time you get a candy out of the machine, you're measuring, is this candy a success? Is it orange or is it not orange? So I guess the point I'm trying to make here is we're conducting a binomial experiment. Just taking one sample of 25 trials or getting 25 randomly selected candies and measuring, are they orange, yes or no? This is a binomial, an example of a binomial experiment. So you need to know that whenever you're working with the sampling distribution of p-hat, this sampling distribution comes from doing a binomial experiment on the population. And so here we've got N equals 25 trials in a sample. And of course, we're measuring whether or not the candy is orange or not. P is the actual percentage of candies, of orange candies in the machine. And every time we draw a random sample, we get a value of p-hat, which is the sample percentage of orange candy. Okay. All right, fine. So going back over here, look what we did, or look what the app did for us. We've drawn a total of 100 random samples, all of the same size, N25. And each time we've had the app collect a sample, it's also collected a sample percentage and graphed that sample percentage as a dot on this dot plot down here, which if we make the number of samples large enough, larger than 95, we'll get a good this dot plot will be a good approximation of the graph of the sampling distribution, okay? So remember that sampling distribution is the entire collection of sample percentages obtained from all possible samples of size, in this case 25. So, and if you take that list and you graph it as a dot plot, you're getting the graph of the sampling distribution. You're going to get the same shape as what a histogram or relative frequency histogram for the sampling distribution would look like. Okay, and we've tried to approximate that with 100 total samples here, and this so far, this is what the shape of the approximation of the sampling distribution graph looks like. I must be making people dizzy with my talk, and I apologize. Let's change this now to 900. Let's have it take 900 more samples and plot 900 more dots on the graph. Okay, so it doesn't look like much of a dot plot here, but that's because we have 1,000 dots on there. And you can see, for example, right here above 60% that there was a number of samples, close to about 120 samples, close to 120 sample percentages that were equal to 60%. So this shape of this graph, if you could put a smooth curve over that, that's going to give you a normal approximation, or it'll be approximately normal. Did you notice that? And also, if I click on summary statistics here, I'm getting what the mean and the standard deviation. And what is that mean and what is that standard deviation? Well, remember that sampling distribution is the entire list of sample percentages. And if you have that list of percentages and you take the average of that list with just the regular old average formula, you're going to get this number, at least with the 900 or the 1,000 samples we did for the mean, and you're getting this number for the standard deviation of that list. And that reminds me that unfortunately we're going to introduce 2 new symbols associated with the sampling distribution of p hat, and here they are. You've got this symbol right here. And how do you pronounce that? You pronounce that symbol mu sub p hat. The p hat here is subscripted, so that means it's the p hat is typeset below the same line that the mu will fall on. So mu subscripted p hat, or mu sub p hat. That's how we pronounce this symbol. And this is the symbol that we're using for the average of the sampling distribution. Or if you have the entire list of sample percentages, that entire collection, and you take the average of that list, you're getting a number called p hat. I'm sorry, mu sub p hat. Furthermore, the standard deviation, this is called, or pronounced sigma sub p hat. This is the symbol we're using for the standard deviation of the sampling distribution. So once again, if you have this entire list of possible sample percentages from all the possible random samples of the same size, and you take the standard deviation of that list using the regular old standard deviation formula introduced in Chapter 3, you're going to get some number that we refer to as sigma sub p hat. Now you may be wondering, why in the hell do we need new symbols? And the answer to that is, well, we're going to need to be able to distinguish between these 2 symbols and these 2 symbols. And so unfortunately, since we're doing like a college level class, we got to get the students into the fine print a little bit, and you got to like open the hood and like look at what's in there, and you got to do a little bit more than look at what's in there. So that's what you got to do in this class. But I want you to notice that, let's go back to this. This graph is a pretty good approximation of the sampling distribution of p hat for this binomial experiment. And notice the value of the average of the list of 1,000 percentages that we got from our 1,000 samples. That's pretty darn close to 50%. which is the actual value of P, the actual value of P, or the value P, the actual percentage of orange candy in the machine. So here's what I'm trying to get you to see. 3 things. 1, this approximation of the sampling distribution graph is normally distributed or bell-shaped. The other thing I'm trying to get you to see is that this approximation, or this list of sample percentages, 1,000 sample percentages, has an average of about pretty darn close to 50%, which is nearly equal to the population percentage P. And so what you're seeing there, using the new notation, what you're seeing in the graph is that the center of the sampling distribution along the x-axis, this value, 50%, that the average, I'm trying to get you to see that the average of the sampling distribution is equal to the actual percentage. And that's not a coincidence. And of course, there's a third thing. And that third thing is about the standard deviation. Well, I'm going to go into that in a second. Right now, I'd like to ask the class, have I lost you, or where can I get you back? What questions are you having? And where's the top of this pen? So far, so good? Did I lose you? All right. Let's go over here. Okay, so if you read in your book, this textbook gives no mention of what's called the central limit theorem, or CLT. This theorem, the proof is not in the book, in this book, and you'd be hard pressed to find it in a lot of books that are higher up. But you can find proofs of the central limit theorem, and this theorem is a proof of the 3 properties of sampling distributions. And this is what I want to talk about now, because we're going to use these properties to develop the theory that's used to estimate values of parameters with statistics, and also be able to gauge how good of an estimate we got. And not only that, but we'll use the central limit theorem to develop the theory and the formulas that are used to do the hypothesis testing problem, which is nothing more than a process that helps you make a decision about the value of a parameter based off of what you saw in a random sample. So I don't know if you're familiar with that. What's that one meme, the internet meme where it's like the guy that's doing this, like, wow. When you get to this chapter, that's pretty much when you do that with the meme. All right, so let's talk about the central limit theorem. The central limit theorem is not mentioned as the central limit theorem in this book, but there's no getting around the 3 properties without there's no getting around writing a book without using the 3 properties if you're going to describe and define what a sampling distribution is. So she does do that. Yes, the Jackie Chan, the Jackie Chan meme, okay? I'm pretty sure that the student who originally came up with that meme was a student in this class. But I don't know, it could just be hearsay. All right, let's take a look at this. So the central limit theorem, it's a proof, and you have to have senior level knowledge or a graduate level knowledge of a math background to understand the proof and to convince yourself of the proof. Although it's easy to use simulations like this applet to convince people that it is true. I know that when I was in graduate school, they sent us out to get random samples and actually try to get an approximation of a sampling distribution. And of course, lo and behold, all three of these properties held every time, for each and every student who got different random samples. Okay. Nevertheless, let's talk about the three properties of the sampling distribution of p hat. And property number one is just described by this equation, that mu sub p hat is equal to p. What in the world does that mean? It means this: the average of the sampling distribution. So, right, if you have the entire collection of sample percentages, all drawn from samples of the same size, that average of that list, mu sub p hat, will equal the actual percentage. Not only that, but when the graph, the dot plot of the sampling distribution is normally distributed, the normal curve will be centered at P, at mu sub P hat equals P. So understand the difference between these two symbols. This is the symbol that is used for the average of the entire list of percentages, sample percentages. And the central limit theorem is a proof that says that this list of, that the average of that list will equal the actual percentage of the population. And moreover, when the graph of the sampling distribution is normally distributed, the normal curve will be centered at mu sub p hat equals p. So the graph of that looks like this. It's the graph of a normal curve. And the x-axis is now going to be a p hat axis. Okay, that's kind of confusing, I think, for students. But here's the reasoning behind that. Okay, go back to, remember this dot plot over here. We had 1,000 samples, and so we got a list of 1,000 sample percentages. This 1,000 sample percentages was not the entire collection of sample percentages, but it's giving us a pretty good approximation of that list. And one way I can tell that is because the mean of the sampling distribution, mu sub p hat, is reported to be awfully darn close to the actual value of p, or the actual percentage of orange candies.
So are those two terms essentially or those two symbols kind of interchangeable then? Mu sub p hat and p?
I would say they are interchangeable, but they represent two different things, but there's two different things that are equal, right? So, I think you could, I don't think there's anything wrong with interchanging them. But I think one of the reasons why we use the notation is this. Mu is used for an average, and of course, if you actually did have the collection and take the average of the collection of percentages, you would get the population mean of percentages. And what was the other thing? And the theorem proves that that number will be equal to the actual percentage. The thing I was going to say was, whenever we describe a normal curve, there's really only two things that you need to describe a normal curve for a normally distributed variable x, and that is the mean, the location of the center, and the value of standard deviation, which controls the height of the peak for the normal curve and the spread, how far spread out it is, whether it's narrow or whether it's more widely spread out. So Mu is a symbol that's commonly used to represent the center of a normally distributed curve, because for a normally distributed curve, the mean will always be this value here in the center. But when and that's for a random variable x, which is normally distributed. But when it comes time to examining the sampling distribution of p hat, the value of p hat is now a random variable. Okay, when I go out and get a sample, I'm going to get a different value of p hat in almost every sample, and that's because sampling variability says that is the case because I'm getting a different sample. But in the context of this problem, p hat is a random variable, and all of the possible values of p hat will be along this x-axis, this p hat axis, just like it was in the dot plot here. And it'll be a normal curve under certain conditions, which we'll talk about later. And that normal curve will be centered at mu. Right? Every mu sub p hat, which is also equal to p. So you can, yeah, so the answer to your question is yes. So we were talking about the central limit theorem. It's a proof of the three properties of sampling distributions. Property one, the center of the graph of the sampling distribution will be this number right here along the p hat axis, and it'll be equal to the actual percentage. And this is good news. And that only happens, but that at the same time, that only happens when the graph of the sampling distribution is normal. That's when the sampling distribution is centered at P. Okay, that's the first property that the central limit theorem proves. Any more questions about that? It's a lot to take in. And property number two is this formula right here is proven in the central limit theorem. And that property just says that this number, sigma sub p hat, which is the standard deviation of the entire list of sample percentages that make up the sampling distribution, that number, it turns out it's equal to the same number that comes out of this formula, the square root of p times 1 minus p over n. And so if you go ahead and you go back to the example, we have an approximation of the sampling distribution graph here with the 1,000 samples. And we also have an approximation of the standard deviation of that list. Okay, they found the standard deviation of that list, and the report from that, the report of that approximation is that sigma sub p hat is 0.1 or 10%. So the simulation tells us, hey, the approximation of sigma sub p hat is that. And if you go over to the central limit theorem, it tells you, well, another way to find this number, or a good approximation of this number, instead of finding the standard deviation of the entire 1,000 sample percentages, you could just use this formula right here. And so that would tell us that sigma sub p hat was equal to the square root of p was the actual percentage of orange candies was 50%. And so then 1 minus p will be 1 minus 0.5, which is also happen to be 0.5. And that's divided by 25. Now notice also that the 25 is under the square root. Okay, so where's my calculator at? Oh boy, here is it still up? Come on, Tim. Oh my goodness, we need to go on a break here pretty soon. Second quit to go back to the home screen. So now I'm going to press second x squared to get my square root symbol. See it? And now I'm doing 0.5 parentheses 1 minus 0.5 close parentheses, and then divide that by, in this case, 25, and I'm getting the same number that we got, that the applet got. And how did the applet get its number? It had the list of 1,000 sample percentages. It found the mean of that list and used that mean along with the standard deviation formula introduced in chapter 3 to get this approximation, which you can see came right out of the formula as being the same thing. So it's not a proof of this property of the central limit theorem, but it's an illustration of it, okay? And then finally, the third property that the central limit proves, the third property of sampling distributions, is this, what's called the normality conditions. Under what conditions is my sampling distribution approximately normal? Because if the sampling distribution is not approximately normal, then this formula here doesn't hold, and neither does the previous formula here hold. So these two formulas only hold if the sampling distribution is approximately normal. So then a part of a section of the proof will show under what conditions the sampling distribution is normal. And right now we're talking about the sampling distribution of p hat, but in chapter 11 we'll be talking about the sampling distribution of x bar. And when we go back and reread the three properties of the sampling distribution of x bar, they'll be slightly different, and your normality conditions will be slightly different than it is for the sampling distribution of p hat. I guess I'm illustrating why this is one of the worst classes you can take in college, but honestly, I'm only saying that because those are opinions I've heard, and my feeling and my opinion is this is one of the best classes you can take in college because, as we all know, you don't always get the real world stuff you need to get for job training in college. But the theory in this book and the books that are stats books that are above this are used all the time in science and technology and government. And plus you're always, whether or not you're going into any of those industries and actually using these methods that we present in chapters 8 through 17, it doesn't matter. You're always being barraged with statistics. You're always reading about statistics on Twitter, on wherever it is you get your news, wherever it is. And you always want to question, where did they get that data? Where did they get those results? Are those results accurate? And are they in line with the mathematical theories that were proven in this class? And a lot of times these estimates that you get will be based off of the theories that are presented here in chapters 8 through 17. So that's that. But anyway, going on with your normality conditions. We're talking about the sampling distribution of sample percentages, sampling distribution of p hat, the entire collection of p hat. And whenever you go out and try to approximate that sampling distribution, you're taking a binomial experiment, or you're conducting a binomial experiment. And it turns out from inspection of a number of binomial distribution graphs, histograms, probability histograms, and then it was proved later, well, the estimation was proved that this is true. Your sampling distribution will be normally distributed if both n times p and n times 1 minus p are 10 or higher. And this is maybe something we didn't say in the previous section on binomial distributions, but when you go back to binomial distributions, remember that x is the binomial random variable representing the number of successes in a sample. But moreover, if you want to find the number of successes, if you want to estimate the number of successes that you would expect to be in a sample, or the number of successes that you would consider to be typical in a sample, the best way to find that is to find the mean of the binomial distribution. And that's going to be n times p. So it turns out that x is also equal to n times p for a let's see here. I want to confuse people. X is the number of successes in the sample, the binomial random experiment, and x is also equal to, or the expected value for x is also equal to n times p, or p% of n. So when you go back and you look at this normality condition, it says that the sampling distribution is normal if n times p is a number that's greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. What that means is that if the number of successes, n times p, and failures, n times 1 minus p, expected in a sample are at least 10, then the sampling distribution is normal. If you take a look at our example from the candy machine here, okay, the number of successes that are expected in a sample of 25, that's just going to be 50% of 25, which is the same as taking n times p, or 25 times 0.5. And that comes out to about 12.5 orange candies. So we expect there to be around, so the typical number of orange candies in a sample, if the actual percentage of orange candies in the device is 50%, we expect the average number, or the typical amount in a sample of 25 to be 12.5. So the value of n times p, the expected value, or the typical value expected, is 12.5. And moreover, we need n times 1 minus p to be greater than or equal to 10. And it will be, because when you find n times 1 minus p, that's also going to be 25 times 0.5, which is at 12.5. So notice that both of these numbers, n times p and n times 1 minus p, which are again the number of orange candies and not orange candies expected in a sample, they're at least 10. We expect our sampling distribution to be normal. And you can see the approximation of that sampling distribution graph is normal, okay? If we were to change, look at this. If we were to change our sampling size, our sample size, can I reset all this? Let me change my sample size to 5. And let me have 1,000 samples. Let's see what happens. You're still, it looks like, getting a normal curve. So there's even times, many times, where there's times where even when this and this aren't satisfied, you still get a graph that's approximately normal. And I'm sorry to muddy up all these waters, but in fact, other statistics books will list this normality condition. They will list this number 10 as being 5. They'll say that as as long as this and this is greater than or equal to 5, we expect the sampling distribution graph to be normal. And if that's the case, then this is the standard deviation of the sampling distribution, and the sampling distribution will be centered at P, the actual percentage. So our book says it's at least 10, but other books say at least 5. And if you look at a number of binomial distribution graphs, you can convince yourself that this is true. Go back over here to this the junky calculator on my website there. Where is it? It's not junky, it's just kind of clunky. Where is that sucker? Oh my God, we never went on a break. I suck. Okay, here we've got a binomial distribution, okay? Look, it looks normal, right? The graph of this table, okay? The graph of this table, all right, will have a bar associated with each one of these values of x, and the height of the bar will be equal to the percentage or the probability of that value of x. So the graph of the binomial distribution looks like this. And of course, you can see if we fit a normal curve over that, it's pretty darn close. And is n times p and n times 1 minus p greater than or equal to 10 here? Yes, it is. But notice that if I change my value of p, can I change my value of p to say 0.1 and change my sample size to say 5, okay, the graph of the binomial distribution table, this table, it's not normal. It doesn't look like it's a bell-shaped curve, you see. So whenever you conduct a binomial experiment, you're getting a sample percentage, and that sample percentage is a random variable. It's a number that is on the x-axis or the p-hat axis of the graph of the sampling distribution. So, once again, every time, here's your sampling distribution of p-hat, the graph of the entire collection of p-hat. And every time you go out and you conduct a binomial experiment, you're going to get a value of p-hat, which is just going to be some number along the p-hat axis. And it's likely that your value of p-hat will be close to the value of p. But if you examine a number of different random samples, we know that because of sampling variability, a lot of those sample percentages will be different numbers, different values on this axis. Okay? So the central limit theorem, it tells you that when the distribution is normal, the center of the distribution will be at P, and it also tells you that the average of the sampling distribution collection will be equal to the actual percentage. It gives you a formula for the standard deviation of the sampling distribution, and it gives you conditions under which the curve, the sampling distribution curve, will be normal. And another, just real quick, and then let's take a break. Here's a graph. Here's a sequence of graphs. Oh, darn it, we gotta take a break. Here's a sequence of graphs of normal curves right here. And what I did was I set the value of n to 300. So I'm over here. I set the value of n to 300, and I examine the binomial distribution curve for a different, I start to change the value of p hat. I'm sorry, I change the value of p, the actual percentage, away from 0.1. When 0.01, let me get 0.01 was where I started. Oh, darn it. Doggone it. There we go. So when I started, right, here's the graph of the binomial distribution, which this could also, this could also be the graph of of a sampling distribution of sample percentages, notice that when that sampling distribution is centered at 0.1, that yes, we're getting a normal curve. It just looks like a spike, and there's not a lot of variation in that normal curve. Most of the values of p hat are falling close to the actual value of p, and so the standard deviation of p hat will be tiny. But if you start to change the value of p and increase it from 0.01, 1% to 3% to 5% to 10% to 20% to 30%, you'll notice that the two things, I would think, or three things, all the curves are normal. And this is because n times p and n times 1 minus p is greater than or equal to 10 for all of these situations. So one thing to notice about the sequence of graphs here, the sequence of graphs of sampling distributions, is they're all normal. That's one thing. The other thing to notice is the center of the sampling distribution starts to move down the x-axis as the value of p increases, because every one of these sampling distributions are centered at p. Okay, and then the other thing to see, and you can see this in the graph, is that the variation, the standard deviation for p equals 0.1, and again, these are all graphs of the sampling distribution of p hat for samples of size 300, okay? But notice the variation. These curves, as you increase the value of p, those curves are getting more spread out along the x-axis. As the value of p starts to get larger and larger and approach this value, 50%, you notice that the normal curves representing the sampling distribution start to get wider or more spread out along the x-axis. And so what you would expect is that if you fix sample size to be the same and you inspect the series of graphs, we see that whenever the value of p over here is close to 0%, the sampling distribution graph's standard deviation is tiny. It's getting larger as p is increased. So if you keep sample size the same and you increase the value of p, the standard deviation gets larger, and you can see that as the graphs are spreading out, until you get to 50%, where the standard deviation actually is at a maximum. And we use calculus to prove that, but you can see it in the pictures. And then once you keep on increasing, oh, it's a bad rendering, but once you keep increasing the value of p from 50%, you're going to start to see in this sequence of pictures that the graph gets less and less spread out. And so what happens to the standard deviation is whenever the value of p is close to 0 or 100%, then the standard deviation will be really small, which means that you're going to get a really good estimate for the value of p, even if you don't know what the value of p is, as long as that value of p is close to 0 or 1. You can also, but there are ways to get a good estimate for p if the actual value of p is not close to 0 and 1. And you do this by fixing the sample size or adjusting the sample size. And I'll talk a little bit more about that later, but the point here is this. When n is allowed to increase and p is the same, the standard deviation gets smaller. So actually there's 2 points. The first point was that if you keep n, the sample size is the same, and you examine the sequence of sampling distribution graphs, you can see that the standard deviation is smaller for those graphs that are closer to 1 or 0. the other thing so if n is 300, the best estimates or the most accurate estimates of p will come from the graphs, or will come from the cases where the actual value of p is close to 0 or 1. However, if the value of sample size is allowed to increase and the value of p stays the same, the standard deviation will get smaller. And so that means if the actual value of p is 50% or close to 50%, as long as you have a large sample size, you will get a tiny standard deviation, which will result in a better estimate of p. And this happens when your sampling distribution is relatively large. So that was, and then before I go on break, the other thing, I mentioned this before. Skip into my loo, and then let's be done with break. Where is that graph? Here. I want you to notice something. Here's a graph, a sequence of graphs overlaid on the same set of axes right here. Look, these are all graphs of the sampling distribution of p-hat. There's a p-hat axis, and all of these graphs are centered at 50%. But each graph is a different graph because it's a graph of a different collection of sample percentages from different sample sizes. And so the most, when n is 30, we've got this black graph centered at 0.5 that represents the sampling distribution. And notice what happens to the sequence of graphs as the value of n increases. As the value of n increases, and we keep p to be 50%, notice that the graphs of the sampling distributions are getting more and more narrow. So that means the standard deviation of the graphs are narrowing, which means that, or lessening as n is increased. And what that means is if the value of n is really large or large enough, it may not have to be as large as 300, but think about the case 300, for example. Remember, this is just a dot plot of the entire collection of sample percentages, and most of these sample percentages are going to pile up closely around the actual value of p. So if you don't know what p is, and you're trying to get a good estimate of that based off of a random sample, if your sample size is large enough, the standard deviation of the sampling distribution will be so small that it's highly likely, according to the empirical rule, that doesn't matter what random sample you get, that sample percentage you get will be darn close to the actual value of p, and so you're going to get a good estimate of p even if it's unknown. Okay? So I want to propose a scenario to you, and this is a hypothetical scenario, okay? And so the hypothetical scenario is this, okay? You've got 30 people between ages 21 and 31, between and including ages 21 and 30, let's say. That group of 30 people is congested at a bar right now in New York City, where they're supposed to be doing social distancing, but the bar's not necessarily enforcing that, and they're all cramped in and they're in a group right now. Okay, so we got a group of 30 young people in that age group, randomly, let's assume it's a random collection of 30 people. It may not necessarily be that random, but for the hypothetical, assume it's a fairly random sample, or sample that's fairly representative of the population of 21 through 30-year-olds who would even go to a bar. Okay, so in this situation, it's a hypothetical again, but let's assume that the probability that any one person in that age bracket in New York City has the coronavirus. Let's assume that that probability is, I don't know, is 10% low enough for people? Okay. Now, it's a hypothetical. The 10%, I made that up. In reality, how can we get a good estimation of what this percentage is when not everybody has been tested, or maybe not enough people have been tested, or maybe it's because we don't know enough about the virus, and and maybe this also is because of the fact that a lot of people are asymptomatic. They don't show the symptoms of the virus. Okay, so it's a hypothetical. So assume that 10% of people who are age 21 through 30 in New York City have COVID-19. Okay, and even though they're supposed to be doing social distancing through the reopening of the city, suppose you've got 30 people from that age group all piled in at a bar somewhere in New York City right now. What's the likelihood that of those 30 people, half of them are infected with COVID-19? Or what's the possibility that a third of them or 20% of them are having COVID-19? When you go to make this measurement from the 30 people, you will be conducting a binomial experiment. Okay, and that's because you have the four properties of a binomial experiment are satisfied. You have a finite number of trials, a fixed number of trials. In this case, it would be 30. And a trial would be a COVID-19 test. And again, for the test, well, not again, but I should point out that for the test, you don't get 100% accuracy on the results. So even if all this was true, the numbers that we come up with for those probabilities would just be an estimate. And of course, a lot of these estimates, the value of that estimate would have to depend on whether or not the sample was a good representation of the population. But here you would have N equals 30 trials or 30 COVID-19 tests, okay, assuming that the test is 100% accurate, which no test is. In this case, P we said was 10% or 0.10. And X would represent the binomial random variable representing the number of people out of 30 who had COVID-19. So it would be the number of positive test results among 30 trials. So going back to those four properties of the binomial experiment, there's a fixed number, a finite number of trials. That's property one. We're good there. Property two, each trial needs to be independent of each other. I know my properties, but I might be getting them out of order here. But do I have those up? I'll put those in front. Oh, I'm just going to roll with it. The trials are independent of each other, and that's because if it's a random group of 30 people, which that could come into question here, whether or not a person is COVID-19 positive, whether or not the first person tested is positive has no bearing on whether the other tests were positive, assuming this is a random sample. So X is the binomial random variable representing the number of positive test results among 30 And X is a discrete random variable. And that's because the values of X are taking on the numbers 0, 1, 2, all the way up to 30, right? We don't know what the number of X is in our sample, but the value, the X in the binomial experiment represents the number of positive test results, and that can be any number, any whole number between 0 and n, or 0 and 30. And so X is a discrete random variable because if you graphed all of these values of X, they would be isolated points on the number line. They would be separated, okay, not a connected set. And what I'm trying to get at is that even though we would be conducting a binomial experiment, we're not necessarily going to get 10% for the number of, for the percentage of positive test results in R30. And that's because our sample may be different from, it may not be 100% reflective of the population, and because of sampling variability. But X is a discrete random variable, but in our sample, we're going to get a sample percentage, a value of p hat, right? This will be the percentage of positive test results amongst the 30 people in the sample. And moreover, that this number p hat is a number that is taken from the sampling distribution graph. And in this context, p hat is a continuous random variable. And the value, yeah, so I'm just going to write that down. The value of p hat obtained from our sample is a value taken from the sampling distribution of p hat. And like I was saying before, moreover, p hat is a continuous random variable. And that's because the values of p hat can be any number, any number in a connected set, right? If you go back and you look at the graph of the sampling distribution, it's going to be looking like this. And what is this? Remember, it's just a dot plot of all the possible different values of p hat. So even though when you conduct the binomial experiment, even though X, the number of successes or the number of positive test results, is a discrete random variable, when you actually get a sample percentage, that will be a continuous random variable, a number that it's just some number in this connected set of numbers along the p hat axis. And so that means that p hat will be a continuous random variable in the case of the sampling distribution. Okay. I don't know if I'm just going around in circles there. So I don't know if that helps or not, but there's some more muddy water for you, and I'm sorry about that. Did that provoke any questions about sampling distribution of sample? I had a feeling that it didn't. So let's go ahead and have you take the, are you here? Yeah, let's have you take the test. So let's, if you don't mind, if you could enable your web